Okay, so now I want to drive you through the construction of a polynomial optimization, thanks to the moment approach. Like we saw before, that with the max cut problem, we was able to formulate a problem about it, but it's like NP hard to do it, you know. So we want to do relaxation about it. We want to find a way to optimize, and that's thanks to moment matrix. So I don't want to begin with this problem. I prefer begin with a simpler problem, but which will be using two matrix moments. So suppose you have this problem: inf of x1, x2 of x1 plus x2 squared minus 4x1, x2. So what you need to know is like the moment matrix is like just like less or more is sort of relaxation of the stuff. Like you, instead of writing like exactly the stuff, you just take matrix about it that we're gonna call M1, and that when you have M1, when you have only two stuff, x1 and x2 in our case, and so you just need to write like this: 1x1 squared, 1x2 squared, x1, x2, x1, x2, x1, x2, and x1, x2. So this matrix is symmetric, it's semi-positive definite. Like I can use a proof like of the stuff about it, like its immersion, mk of 1, 1 equal 1, mk is positive semi-definite, and for any monomial, we have mkvyw is equal mkvwy. So wait, anyway, what is really important is like it's semi-positive definite, and so the goal here is just to have like M1, you can represent any polynomial with x1, x2, and x1 squared. Like if I wanted also to write x1 squared plus 4x2 squared plus I don't know, like this, it could be written, it can be written to, and if you want x2 constraint, like if you want like x1 squared plus 8 x1, x2, it could work. Like it's just like a relaxation of the stuff, It's like we have like if I write this, like it's just like we have our p star here that will be there, and we have our M1. But the fact is sometimes you can have like more complex problems. Like for example, if we recall about the max cut problems, we had like we could have like x1 minus, if you took only 3 points, minus x2 squared plus x2 minus x3 squared plus x1 minus x2 squared. And so basically it's just like you have 3 variables now, you have x1, x2, and x3. So it will be inf of this. So you will need M2 matrix moments, and M2 is just like you the same like 1 x1, but like it will be bigger now. x1, x2. Well, no, I think like it's like x1, x2, x3, x1, x1, x2, x1, x3, x2, x2, x3, and x3. But yeah, that's not really important. What I wanted to mention you about is like, so for this you will need like the approximation with M1 will not be sufficient, and so you'll need even a bigger set that will be M2, and etc. Like if you have after x1, x2, x3, x4, you'll need the M1, M2, and M3 matrices. So it just like the number of moment matrices is just equal to the number of variables, number of moment matrices. It's just the number of variables, like x1, x2, minus 1. So yeah, that's it. just wanted to drive you a little about it so you understand how many matrices moments you will need normally, generally, to do optimization about it. So the more you have matrix moments, the more you can be precise. So sometimes you'll need to go straight. But yeah, that's this. That's in a way we relax the stuff because you can encode the polynomial in occurrence into M1. So that's it. And so if we continue to try to go with it, so I just write the M1 moment, and if we want to expand the objective function, so it will be better to write. We will know exactly what we have. We'll have x1 squared plus x2 squared plus 2x1 x2. It's not just a remarkable identity. Minus 4x1 x2. And so it's just equal to x1 squared plus x2 squared minus 2x1 x2. So basically we have this, and we can notice that polynomial can be written as a linear combination of the element of the one moment matrix. Like the goal here, we have this, and so we just see x1 squared, here it just represented here, x2 squared, x2 squared is just here, minus 2x1 x2 it can be there, for example, and symmetric, so you have also at the right x1 x2. So yeah, you can just represent them as by relaxing it. But the problem is here, like when you have this, you have some square, and the problem about the square is that you cannot optimize it because they are not convex, and so that's the trick about this matrix moment, is there is a semi-positive definite, but we have a square now, and so to be able to write the square, but the computer does not really know they are squares, we can introduce variables and say, for example, that y11 will be equal to x1 squared, y22 will be equal to x2 squared, and so you just write the indices, so here y101 will be x1, and y02 b2 will be x2, and so yeah, you can just rewrite it basically. So you have everything, and so just x1 x2 will be 1 to 2, so y1 to 2 will just be equal to, just the line on the columns will be equal to x1 x2. So yeah, basically we just rewrite it with this, so the computer does not know we have squares, but because it's semi-positive definite, he will optimize it and all will be squared, and so it will be convex optimization because semi-positive stuff are convex, and we will still have our constraints respected. So if I write this, it will be 1 will still be 1. If we replace, it will be y01, y02, so here y11, y22, y02, it just indices, you can write it as you want, that's how we want to write it. So y01, so that's what we have. Now we rewrite this, so it just respects our constraints from this, and yeah, so this is just a combination of stuff. So okay, when we have this, as I said you, the stuff is if you take no matter stuff like for example this matrices, or you could have taken this one too, no matter when you took the first stuff, like this one or this one or this one or this one. So I'll take just the one at the at the bottom, at the up left. So this one. And so I just take this, and so if you check about this, it should be semi-positive definite. All four blocks should be positive definite. And if you check so the determinant about it, because it's positive definite, you have y1 that should be superior to y01 squared. And so it just says so that x1 just says that if you check y11, it just x1 squared should be superior to, if you check 01, y01 is x1, and so yeah, it just says this, and so it means the and so it's squared, so it's squared, and so it just means the full square should be superior or equal to the real square. So the computer cannot take any values that will be wrong about it, trying to trick with negative values. He will not be able to do it. And so yeah, you have this, and so solving this problem numerically, you'll find your SDP will just from this, it will just give you this is of course, so the problem will be you retake your steps. So as you said, x1 was x1 plus x2 squared. We just write it like this. So x1 squared is just y1, as we write here. X2 squared is just y22, and finally we have minus 2 x1 x2. It's minus 2 y1 y2, and so you just have this inf of this such that we have this being semi-positive definite. And so if you solve this SDP numerically, because as we say, now we have been able to write it as SDP, and numerically the computer is really good to solve this. He just returned us this matrix. And so basically what we can see is if you check about stuff we want to optimize by, y11, y22, which are here, y11, y22, and minus 2 y1, y2, it will be here too, for example. So you just see it 0, 0, 0, so you just inf of it will be if you replace, it will be 0 plus 0, 0 plus 0 minus 2, 0, and so it's equal to 0. And so we just proved the optimal value of the SDP relaxation is 0. And so if you check your primal here, we have this, because we have this, we just see here it was inf, and when we do inf, we have a lower bound, and so it means p star will be superior to 0. And we can see also that the optimal to the moment matrix actually correspond to the moment matrix for the point x1, x2 equals 0, and so hence p star is equal to 0. And so yeah, what I want to say is this here about is I want to say this because if we regard the simple variables in the first line of our linear solver, y01 and y02, they represent x1 and that represent x1 and x2 that are here. Then if we test the algebraic coherence of it, like x1 is equal to 0, x2 is equal to 0, so the square of them will be just 0, So x1 squared will be equal to 0, x2 squared will be equal to 0, and so it means like y11 equals 0, y22 equals 0, and x1 and x2 should be equal to 0 too, and y112 should be like equal to, like, it's equal to 0, so y12 equals 0. So it's literally like our mapping from x to y in a way. Our mapping here, just from this to this, is perfectly identical in a way, perfectly coherent at least, with our real points, which are x1 and x2, that are equal to 0. Because our 2 points at the beginning, if we check about it, it's just like x1, x2, and so if we replace it really by the values they get, we really have exactly what we find here with the moment matrix, and so it's perfectly current, and so the computer does not have cheated. He was not like we found the good point about it. It's really the optimal minimum, and because the computer could have cheated. We have here solutions that touch exactly our frontier on our original curve, and so the execution is exact. In a way, like you could have like y01 equals 0 and y11 equal, like, we could have this, like, we could have like 0, 5, instead of 0 for y, or like x being 0 but y having some y equal to 0, 5, and so we could be like, oh, it's not working, but it's not working. It's not exactly the perfect solution, but we should have respected the semi-definite programming, because 0 point squared, 0.5 is equal to 0 squared, and our determinant would be positive. Yeah, it just means that the solution would have been just matricial and not physically realizable, and so it should have been a solution, less or more of a solution, but it would have read, and it's just like hierarchy stuff, it should still not have been exactly the good point, but it just means we need to take a second moment matrix, for example, go to the second level of the moment matrix, because it's M1 here, but for example, if you take the stuff we just showed before about the max cut problem, then you need M2, because with M1 you have this problem, and so if you take just M2, then after you can like converge, really, like, because the level 1 gives an optimal value of 2.25 but does not converge, and the level 2 gives the real value, the optimal value of 2 for this problem. And so that's globally about it. Maybe I can add some stuff, I don't know. Like, I just feel I've said less or more everything for now about it. But yeah, maybe a last thing that we can say, like, as I said, so p star is equal to, and that's the actual minimum, because it's respecting like c or y stuff, and x and y you just show it's equivalent, and so we can also say that's really a beautiful stuff about this SDP, because we just found out here the proof of an arithmetic geometrical inequality, in the sense that our initial program was this, x1 squared plus x1 plus x2 squared minus x for x1 plus x2, and so we just proved like it's also, the actual minimum is 0, so this, it means, is superior to 0, so we have this, and so because we have this, if we pass this if we pass for x1 x2 in the other sense, it will be equal to this, And so if we take the square about it, you have x1 plus x2 is superior to 2, or like if you want it to me do it slowly, it's like this, and so this is just equal to 2 x1 x2, 2 to the square x1 x2, and so basically it just means that we have x1 plus x2 divided by 2 is superior to the square of the root square of x1 x2, and that's literally saying that like if you say like check at the left, it just arithmetic average average stuff, about something, like you have two apple on what the stuff, like you divided by 2, and here it's just the geometrical average. So it's just proving that without any demonstration, classical algebraical, without any demonstration of classical algebra, the computer just showed like the geometry of semi-positive definite matrices with like just using the semi-definite positive geometry of matrices instead of algebraical or classical demonstration. We just prove one of the most fundamental theorem of mathematics, which is the inequality, the arithmetical geometric inequality, where we saw that where we just saw that the average arithmetical stuff is always superior to the average geometrical stuff. And so just to say that SDP is just not a tool for engineers to find value, but it can also like find really fundamental mathematical theorems. So yeah, that's it.